We'll see what it really says precisely. But for our purposes, right now, if you were speaking at the level of a cocktail party, you would say, well, what the central limit theorem says is every distribution is a normal distribution. Everything tends towards the normal distribution. Not that everything is normal, but it tends towards the normal distribution in a certain sense, right? So it's not just that it occurs in many, many, many different places. The theorem says it should occur everywhere, and for a particular reason. Okay, so that's what we'll talk about today. Okay, so before we do that, let's talk about continuous probability. So we have to talk about continuous random variables. Okay, so far we talked about discrete random variables, meaning things like integer random variables, where they take on discrete values, right? Integer values, 1, -1, 2, 3, 4, etc. Now we'll talk about continuous random variables, meaning, so we'll have a random variable x, which takes on values on the real line. So for example, we might have a continuous random variable which takes on values in the interval between 0 and 1. So it can take on it can be any real number r between 0 and 1. Right? Okay, so now, if we have such a situation, and it can where our random variable can take on any real number value, we certainly cannot ask the question, or it's not very meaningful to ask, what's the probability x equal to r? Right? This is not a very interesting question, because usually this will end up being 0. Right? So instead, the kind of question we'll ask is, what's the probability x lies between a and b? Right? So we'll have some interval a to b, and we'll ask, what's the probability that x sits inside this interval? Okay? So these will be the events for our probability space. Now, let me just say something at the start. If you want to understand what the sample space is for these random variables, you have to read the notes. Because I'm going to be trying my best to sweep this, the details under the rug. Right? Because we are trying to cover this in one lecture, and so I don't even want to give you a chance to get confused about it. Okay? So if there's anything confusing, it's been suppressed. Okay? All right, so this is the kind of, these are the kinds of questions we'll ask. What's the probability x is between a and b? Okay, so now, let's say that our probability distribution was uniform between 0 and 1. So we had an equal chance of picking x anywhere between 0 and 1. Okay? Well, it turns out that the way to describe this distribution is in terms of what's called a probability density function, a PDF. Okay, so in this case, it's a function, f of x, and the function for this uniform probability distribution is just going to look like this. So here's 0, here's 1, there's the real 9. And the function is going to be 0 outside of this interval 0, 1. And up here, it's going to take on the value 1. So that's the function value, right? So the function looks like this. It's 0 everywhere else, and it's 1 between 0 and 1. Okay? Now, what's the useful property of this? The reason that this is how we define the probability density function here is because the area under this curve equal to 1. Okay, so let's do this first by example, and then we'll do it, and then I'll give you the properties of f. So suppose instead, now our random variable x takes on values between 0 and L for some L. Okay, so now here's 0, here's L. Okay. And now f of x, which is the density function, is going to look like this. It's going to take on value 0 outside of 0 through L, and its value is going to be how much inside of this interval? 1 over L. Okay, so the properties are f of x has to be greater than or equal to 0. Integral from minus infinity to infinity of f of x dx equal to 1. So the area under the curve has to be 1. That's this one. The probability x is between a and b is integral from a to b of f of x dx. So you want to know what's the probability that x lies between a and b. You just look at the area of the curve between a and b. Right? Okay. So let's work this. Okay. So then let's work out some of these. Okay. Now we can also draw an analogy with discrete random variables and figure out what's the expected value of x. But what should the expected value of x be? By analogy with discrete random variables. Okay, so if it takes on value between a and b with probability integral between a and b of f of x dx. So now, what about if we said, what's the probability it takes on value between little x and little x plus delta x? Right? Well, this area, it should be this area, which is f of x times delta x, because delta x is now small. Okay. And now if you want the expected value of x, you want to multiply this by the value of the random variable there, which is x. So you get x times f of x dx, integral from minus infinity to infinity. Right? What does this correspond to? In the discrete case, this corresponds to summation. Right? X equal to minus infinity to infinity, x times probability. Let's call it a equal to a times probability, x equal to a. Right? Same thing here. Right? The probability of x equal to a is replaced by a probability of x is between little x and little x plus delta x. Right? Same thing here. Right? And we are replacing the summation by an integral. How about the variance of x? Well, there are two ways of doing it. You'd write equal to integral. Okay, if this expected value of x equal to mu, then you'd write the integral minus infinity to infinity, x minus mu whole squared, f of x dx. Right, it's the expected value of x minus the mean whole squared. Right, so, but then you remember you have this formula which is always expected value of x squared minus expected value of x whole thing squared. So you could write the same formula down again in the continuous case. What's the expected value of x squared? Right, you just do integral minus infinity to infinity of x squared f of x dx. Okay, so let's try to actually compute these and see what they are saying. Okay, so and I'm not sure how long it's been since you've done calculus, but certainly you've done it much more recently than me. So this should be easy for you. Okay, so first things first, we want to say, well, integral minus infinity to infinity of f of x dx equal to 1. Well, in our case, it's integral 0 to L of 1 over L dx, right? And that's just 1 over L x between 0 and L, which is 1. Okay. What about the expected value of x? Is integral x times 1 over L dx from 0 to L. Okay? So integral of x is x squared over 2. So you get x squared over 2L between 0 and L. And what do you get? L squared over 2L, which is L over 2, which is what you expect, right? So if you have a uniform distribution between 0 and L, the expected value is L over 2. Now we want to compute the variance of x. So we compute the expected value of x squared, right? And that's just integral 0 to L x squared times 1 over L dx. So x squared, the integral is x cubed over 3. And we just carry the L across between 0 and L. So you get L cubed over 3L, which is L squared over 2. Right? But that's just the expected value of x squared. L squared over 3. Oh, sorry. L squared over 3. See, I said you had an advantage over me in calculus. Okay, so variance of x is expected value of x squared minus expected value of x whole squared, which is what? We just computed expected value of x squared. It was L squared over 3. And then what's expected value of x whole squared? This squared, right? L squared over 4. So L squared over 3 minus L squared over 4 is L squared over 12. And so the standard deviation is L over square root 12. Now, where we got the square root 12 from, or the 12 from, well, that's just a calculation. But what this tells us is the variance is proportional to L squared, and the standard deviation is proportional to 12, which is what you'd expect in a uniform distribution. Right? You'd expect to be about L far, constant times L far from the mean. And that's what this is telling us. Okay. Okay, so now, where do we go to next? Okay, so now let's look at two different probability distributions, which are, so before the two distributions we look at are the normal distribution and the exponential distribution. Okay, so okay, so let's go back and talk about what makes probability, these probability distributions special. So we talked about some distributions already. We talked about distributions like the binomial distribution, the geometric distribution, the Poisson distribution. And in each case, what we said is that that there's, okay, so maybe I didn't say it quite so explicitly. So let me say it explicitly. So what is it about these distributions that's so interesting? Well, the interesting thing is that probability theory tells you that there's a certain way in which you can look at the world which makes it much easier to understand. Okay? Now, there are already certain ways that you've looked at the world. So you learned geometry when you were, well, I don't know what age you were when you learned geometry, but it certainly changed the way you look at the world. It makes it possible for you to understand the world around you because it's made up of shapes and lines and so on and flats of, planes and etc. And you think in terms of coordinate axes and so on. It makes it much easier for you to understand the world around you. Now, probability theory does that, but it's done that, to an even greater extent. Okay, and so what's this probabilistic view of the world? So the probabilistic view of the world is that, beneath this, beneath the world as we see it, you should think of there as being lots of little demons who are sitting around tossing coins. Okay? And the world that you see is the result of these coin tosses. Okay, now, you might say that makes no sense. That's just utter nonsense. Yeah, but it's really true. I mean, it's true that this table which we think of as solid, it's not really solid, right? There are elementary particles sitting in there, and they are jiggling around at random. Okay, or the air we breathe. I mean, it's little molecules of air that are jiggling around at random, and they could, there's a small chance that all those molecules of air could be sitting in that back corner up there. And then we'd be in real trouble. But the reason we are not is because there are certain, probability distributions have a certain shape to them. And so what these probability distributions are that we are studying are the fundamental shapes, through which probability asserts itself. And so what we are saying is that there are certain very, very basic probability distributions, and the phenomena that you see around you are the results of these probability distributions. And so if you recognize these shapes, you have a better chance of understanding the world around you. Okay, so what are these shapes? So let's look at one more probability distribution, which is the exponential distribution. The exponential distribution is the continuous analog of the geometric distribution. So in the geometric distribution, there's one parameter, which is P, the probability of heads when you toss a coin. And then what does the geometric distribution ask you? It says, how long do you have to wait till the coin comes up heads? Right? So the geometric distribution is a discrete probability distribution where you say, how many steps do I have to wait for something to happen? Okay? Now, the exponential distribution has a single parameter lambda. And now, there's no number of steps that you're waiting. You're waiting for a certain amount of time. And the time is a real random variable. Okay? And so, what are you waiting for? Well, it depends upon your particular interest. You might be waiting for radioactive decay, in which case you're saying, well, how long do I have to wait before this particle decays? Right? That's a random variable, and it could decay any time. It's not, there's no clock ticks according to which it decays. Or you might be waiting for a system failure. Right? Again, it can fail any time, and so you're just waiting until, what's the time until the system fails? Or maybe, perhaps you live in California, and so you're waiting for the next earthquake. Okay, again, this can happen any particular time, and so, right? It's, or possibly it's close to finals, and you're waiting for the next fire alarm at UC Berkeley. Okay, again, this is a random variable, and it can happen anytime. Okay, so So these are all exponential random variables with parameter lambda. And now, okay, so we can describe this probability distribution in one of several ways. So we can say, here's the probability density function, f of x. It's lambda times e to the minus lambda okay. So the probability density function sort of looks like this. It goes down exponentially. Okay. And now what we want to figure out is, well, what's the expected value of x? What's the variance of x? Okay. It turns out the expected value of x is 1 over lambda. And the variance is 1 over lambda squared. Okay. So now each of these three facts, the fact that this is a probability density function, the fact that this is the expectation, the fact that this is the variance, each of these is an integral to be evaluated, right? So the fact that this is a density function, well, you have to check that it's at least 0, right? It's never negative, and that's completely clear. And you have to check that the integral from minus infinity to infinity of this is 1. Okay, so before we check that, let me just state the write out the density function more accurately. It's lambda times e to the minus lambda x for x at least 0, and it's 0 if x is less than 0. Okay, because it's in the exponential distribution, we are asking what's the chance that we wait for this amount of time, right? And so our waiting time is always going to be a non-negative random variable. And so it's 0 before this, and it's exponential like this. Okay, so let's do something. Let's take a 1-minute break during which you figure out whether you can actually, how you would actually evaluate these integrals. Maybe let's take more than a 1-minute break for that. 2-minute break. Okay. Oh, I see. Okay. Okay, so let's see. So let's just figure out how we do this. So first the integral of so what's, how do we figure out the expected value of x is 1 over lambda? Well, it's just integral of x times lambda e to the minus lambda x dx, 0 to infinity. And now we just have to do an integration by parts. So we call this f and we call this function g, right? And then we do our usual integration by parts. So we write this as x times the integral of this. Okay, but what's the integral of this? Lambda times e to the minus lambda x. Right, this is almost the derivative of e to the lambda x, e to the minus lambda x, so you get minus e to the minus lambda x. Right, so, and then minus derivative of this times the integral of that, so we'd get integral of negative of that again, so negative e to the minus lambda x. Right, so the second time we just take the derivative of x, and so it disappears here. This is 0, and here we get e to the minus infinity 0, and e to the 0 is 1. Okay, so sorry, what did I... okay, you should know your calculus better than I do, so yes. Oh, you integrate it, yes. So, okay, so when you integrate it, you get... I'm sorry?
Minus 1 over lambda.
Is that what you get? Between 0 and infinity. Should there be a minus on the step above? Yeah. Okay. Yeah, but shouldn't there be a minus, but then don't I get another minus from this? No. So sorry. Don't you take? Sorry.
That's right.
Yeah, it's okay. Okay, good. No, I don't, I don't doubt that it should be questioned because it's been more years than you would imagine since I've done calculus, but I think it might be right. Okay, so we are, e to the minus x minus infinity is 0, and then we get plus 1 over lambda. Right? Okay, good. Now you can do a similar calculation for the variance, and you can do a similar calculation for just that the probability is 1. Okay. Now that's one way to look at this whole thing. There's another way to look at this, and the other way you would look at this is you would just say, look, let me think of this process as a continuous analog of the geometric distribution, right? So now, again, let me think of it as, Well, behind the scenes, there's a demon who is flipping a coin at every moment in time. Right? So let's say that the demon is flipping the coin every delta units of time. Okay? And so what's this lambda now? Well, the lambda is the number of heads you should get per unit time. That's the expected number of heads you get per unit time. Okay? So if this demon is flipping a coin every delta units of time, what should the probability of heads be? So shouldn't it be delta times lambda? Yeah? Okay, so that's the probability of heads. And now, what's the expected waiting time for the first heads? It's 1 over p, right? Which is okay. So what do I want to do? Let me instead figure out what's the probability that W is at least some number t. Okay. So out here it should be 1 minus p to the t. Right? It should be okay. It should be 1 minus p to the power of t times delta, t over delta. Right, so if I'm waiting for t amount of time, and I'm flipping this is the amount of time, 0 to t. This is how long I want to, I'm saying, what's the probability heads doesn't occur during this time interval? But now I've taken the time, every unit of time, and I've divided it up into small little delta intervals, right? So how many times did I actually flip the coin between 0 and t? Right? There was 1 over delta many coin flips in this unit interval, and there are t different intervals like this. So it's t divided by delta. That's the amount of time I'm waiting, right? So this is 1 minus delta lambda to the power of t over delta. Okay? Now delta is tending to 0. Delta lambda is tending to 0. Okay? Now, there's a very useful formula that you should know, which is 1 minus x to the power of 1 over x tends to e to the minus 1 as x tends to 0. Okay? So we can put this in the form 1 minus x to the power of 1 over x if we just write it as 1 minus delta lambda to the power of 1 over delta lambda, right? Except that we don't have 1 over delta lambda here, but we have t divided by delta. So let's just make it 1 over delta lambda times whatever it takes to make it t divided by delta. So it should be t times lambda. Right? In fact, when we write it like this, we could also write it like this raised to the power of t over t times lambda, because when you raise this to the power of that just multiplies out here. But this is e to the minus 1, because we are now going to let delta tend to 0, because this demon is going to start flipping coins more and more often, right? And so this gives us e to the minus lambda t. Okay? This is a property of the exponential distribution, that the chance that you have to wait at least t, the chance that x is at least t is e to the minus lambda t. So how would you see this directly from the formula? Okay, so this was one way of seeing that the probability that x is at least t is e to the minus lambda t. Okay? So now you can see why it's an exponential distribution. the chance that you have to wait for this amount of time before the event occurs goes down exponentially, right? With this parameter lambda. That's the parameter of the probability distribution. Another way of doing this is doing it directly in terms of the density function. So you'd say, well, this quantity is integral of what? Well, what's the probability x is at least t? Well, there's t. The probability x is at least t is the area under this curve here, right? Which is just the integral from t to infinity of f of x. So integral from t to infinity of f of x dx, integral t to infinity of lambda e to the minus lambda x dx. Which is what? E to the minus lambda x. Negative. Right? It's e to the minus lambda x minus e to the minus lambda x over lambda, and then times lambda, so those cancel from t to infinity. At infinity, this is 0. Right? And at t, you get e to the minus lambda t. Right, so this is telling us that the way we got this exponential distribution, we could see it also as a limit of the geometric distribution as our coin flips get closer and closer together. As we flip coins, more and more coins, and we flip them in smaller and smaller time units. Okay. Okay, so this distribution is extremely useful when you're trying to figure out what's the time to, a time until a certain event occurs. And usually it comes up because you want to figure out time to failure for a system, right? Any kind of such event that occurs after a long period of time, but you don't know when it'll occur, and you have a this is the distribution that actually describes that. Okay, now okay, let's talk about one last distribution, which is the normal distribution. And we'll say that a distribution is standard normal if the probability density function f of x is 1 over square root 2 pi e to the minus x squared over 2. Okay? So what does this distribution look like? Well, the first thing you can see is if this is x, it's symmetric in x, right? E to the minus x squared over 2. So since it's x squared, whatever it looks like to the left, it must look like to the right. Starts off at 1, does it? At x equal to 0? No? No, 1 over square root 2 pi. Oh, good. Yeah, it shouldn't have started at 0. And then it starts falling off. And it falls off exponentially, not just in x, but in x squared. Right? Okay, so now there are a few things that are worth noting about this distribution. Let me just give you these figures. So the first thing, okay, so So why is this called the standard normal? Because the expected value of x here is 0, and the variance of x equal to 1. Right? So sigma equal to 1 and mean equal to 0. Okay. So now this is considered the standard normal because we've made the mean 0 and the standard deviation 1. And so if you plot it out, here's 1, here's minus 1. So 1 over square root 2 pi is about 0.4. So that's about the height of it relative to the standard deviation, which is 1. And then if you look at the area between, which is within one standard deviation, this is about 0.68. Okay, so plus minus sigma, you get 0.6827. Plus minus 2 sigma, you get 0.9545. And plus minus 3 sigma, you get 0.9973. Meaning that as you go out, here's 1 sigma, 2 sigma, 3 sigma, right? The area under the curve outside, gets very, very small very quickly. Okay. Okay. Now, okay, so there are a few things to understand about this. So first of all, I said that this was a standard normal distribution. Now, what you can do is you can also look at the normal distribution which has mean m, mean mu, and standard deviation sigma for some general mu and sigma. And then the probability density function just becomes f of x equal to 1 over square root 2 pi e to the minus what? Okay. So if you want to change the mean to mu instead of 0, all you have to do is take this curve and translate it by mu. Okay, so how do you do that? You change x to x minus mu. Okay? And then, if you want to change the standard deviation from 1 to sigma, all you have to do is, again, rescale x by sigma. Right? So, divided by sigma squared. Okay? So this is normal mu sigma squared. Okay? This is the distribution it's distributed like normal mu sigma squared. Okay? Yeah.
Where's the 2 or
2 sigma squared. Okay, so a few different things about this. First of all, anybody know where the 1 over square root 2 pi comes from? I'm sorry? Right, yeah. So that comes from saying that the integral has to be 1. Okay, so that's the way the 1 over square root 2 pi came from. So if you look at the integral 1 over square root 2 pi e to the minus x squared over 2. Okay. If you just look at this, you'll get square root 2 pi. Anyone remember how one shows this? Yes. I'm sorry? But how do you compute this integral? Yeah. You do a power series. Maybe, that's one way to do it. It's, yeah. Yeah, you switch it into polar coordinates. So, okay, so let me just give you the, because all the steps are a little too laborious, you should be able to reconstruct some of them. But let me just tell you how just the outline of it. So you'd say A equal to this, and now you'd say, well, let's compute A squared. Okay? So what's A squared? Well, somehow it's easier. It's integral minus infinity to infinity, e to the minus x squared over 2 dx, integral minus infinity to infinity, e to the minus y squared over 2 dy. And now these are integrals. They're like summations, so you can, you can use the distributive law and you can pull this all in. So this is just the double integral minus infinity to infinity, minus infinity to infinity, e to the minus x squared plus y squared dx dy. Okay? All right, so you're integrating over the entire now two-dimensional plane. But x squared plus y squared is like r squared, right? If you switch to polar coordinates. So you want to write this as integral e to the minus r squared. And now you want to change dx dy to dr d theta. Right? So you want to write this as dr d theta. R goes from 0 to infinity. Theta goes from 0 to 2 pi. Except for the fact that dx dy is not equal to dr d theta. You shouldn't be integrating with respect to dr d theta because, well, you figure out, you figure out what you're integrating with respect to. Here's your r. And now you think of a little d theta here and dr here, right? And you figure out what's the area of this little piece, right? That's what should correspond to dx dy, right? It's the area of this piece. But the area of this piece is not dr d theta, it's r times dr d theta, right? Because it's as though this is d theta and this is dr, and this is r d theta, right? So it should not be dr d theta, it should be r times dr d theta. And now that you have this r dr d theta, well, okay, this becomes an easy to integrate function. Okay? And once you integrate this, you find that the integral turns out to be very simple, and it turns out to be 2 pi. And that's how you get the integral of that a equal to square root 2 pi. Yeah? It's very clever. Okay. Okay, so now, by the way, any questions? Yeah? Okay. Okay, so now, what does the central limit theorem tell us? What the central limit theorem says is, suppose that you have random variables x1, x2 through xn, and these are independent. They are independent random variables with mean expected value of xi equal to mu and variance of xi equal to sigma squared. Okay. So now we want to look at x equal to x1 plus x2 plus x sub n divided by n. So the sample average. Okay. So what's the expected value of x? I'm sorry? There's somebody who said. Yeah. Anybody? Expected value of x is mu, right? Because it's just the average of the xi's, but each of the xi's has expected value of mu. Right? What's the variance of x? It's sigma squared over n. Right? Well, why? Because the variance of x1 plus x2 up to xn is n times sigma squared. But then when you divide by n, the variance gets divided by n squared. So you get sigma squared divided by n. Meaning now the new sigma is, the standard deviation is sigma over square root of n. Okay? All right, so x is just any old random variable with mean mu and variance sigma squared. You take n copies of it, independent copies, add them together, take the mean. Okay? Now, what's the distribution of x? The claim is the distribution of x tends to normal with mean mu and variance sigma squared over n. Okay? So it doesn't matter what distribution you started with. The distribution you end up with is always normal. So as long as you have some amount of averaging that happens of independent copies, that's the distribution that nature always heads towards. And this is why the normal distribution is so common. Right? That's the importance of the normal distribution. Right? Everything tends towards the normal distribution. Okay? Yeah.
Are x sub i's, are they all also like normal distribution?
No, they're not. They can be anything. Oh. All we know about the x sub i's is that they have mean mu and variance sigma squared. So for example, the x sub i's could be 0, 1 random variables. So they could be probability p of heads, 1 minus p of tails.
Okay.
Right? So what we're saying is, if you take these random variables, you would take their average over a large number, you will always see the normal distribution. Right? And not only does this happen as n tends to infinity, it actually even happens as n tends to small numbers. Right? So it's a really stunning thing. If you actually try this out with distributions which look completely strange. You could have x1. They don't even have to be identical distributions. X1 might look like this. X2 might look like that. You put together a few of these distributions. You take the average. What you get, you get that. Right? It's always the case. The second thing to notice is that the standard deviation goes down as square root of n. Right? So x is distributed like a normal distribution, but the standard deviation or the variance is going down with n, meaning that what's happening is it's getting more and more peaked. Right? As you increase n. Okay, so now here's one way that this is applied in terms of confidence intervals. So let's say that you were tossing a coin, and somebody gave you a coin. They tell you it's a fair coin, but you're not really sure, right? So you don't really believe them. So now, okay, so you toss it 100 times, and suppose it comes up heads 41 times. Okay, should you believe that this is a fair coin? Okay, so this is, when you have something like this, you have to do statistics on it, and you do what's called confidence intervals. Or significance tests. So what you do is, well, you look at the fact that if you want significance 0.95, so with probability 0.95, you're within 1.96 sigma, right? So if you look at the normal distribution, if you go out 1.96 sigma on each side, and then you look at the area outside this curve, then it's 5%. Okay? So now what we'd say is, let's pretend, let's try to test the hypothesis that it's a fair coin, and let's reject, we'll say that in this experiment we've proved that it's not a fair coin. How do we say it? That our experiment is significant in proving that it's not a fair coin if it's outside of 1.96 sigma. Okay, so let's figure it out. For 100 coin tosses, the mean should be 50 because we are assuming it's a fair coin. And what's the standard deviation? So the variance is sigma squared is n times half, npq, right? Which is 100 times half, which is 25. So that means sigma is 5. So 1.96 sigma is 5 times that, which is 9.8. Okay, which means that you expect to be, the mean is 50, and then 1.96 sigma, which means that you should be, with 95% probability, you expect to be between, so with 95% probability, you expect to be between 59.8 and 40.2 heads. Well, the number of heads we saw were 41. At this point, we have to say, we cannot reject the hypothesis that the coin is fair. With a fair coin, we still have a, we still have a 95% chance that we'll get between 40.2 and 59.8 heads. Okay? So the fact that we saw 41 is not so surprising after all. So at this point, we say, this experiment has no significance at all. Right? Meaning that the hypothesis that we were testing, this experiment was, it had no result. Now, what if we, okay, so notice that we can't say that we proved that this coin is fair. We did nothing of that kind. All we can do through statistics is we can give evidence that the coin is not fair, but we can't prove that it is fair, right? Okay?